Okay, section 5.2. We're going to talk about it. Guess what we're going to talk about today, class? Medians.
Wait, do you mean medials? No, I'm just kidding.
All right, let's talk about a median. Now, when we talk about a median, we did talk. Listen, shh, we're ready to start now. We did talk about a road, and the grassy area in the middle of the road is called the median. Okay, in the what? In the middle of the road. Would you agree? So if we talked about the median, shh, guys, you need to settle down. We had our little fun. Let's get serious now. Let's have fun with geometry now. All right. So if I did the median does this. It goes from a vertex. Shh, listen now. It goes from a vertex. Now, what does median mean?
Middle.
You go to the middle. And you talked about that when, like in your lower math class. You remember mean, median, and mode? The median was the number that was where? It wasn't the average. It was the number that was in the middle. Okay, so know what the word median means, and then you should be able to figure this out. Okay, so where does it go? It goes where? To the, where do you think? Give me a better word than middle for a geometry word.
Midpoint.
To the midpoint, right. So let's do this. Let's not use that line right now. Let's, well, I don't want to get super fancy, but I just want to at least find where the midpoint is. All right, so if I scooch over to about right there, that looks about the midpoint, doesn't it? All right, so I'll put a dot right there. So now, look what I'm going to do. There's a lot of talking over there. Let's pay attention, please. We are starting. Come on now. We had our little time. Now's the time to pay attention. So look, we start from the vertex and we go where? To the midpoint, okay, to the opposite side. Everybody see that? So that right there is the median. So the line segment itself is called the median. Let's do the same thing over here. Let's find the midpoint of this side. So that would be right there. So put a dot right there. That's the midpoint. And let's make this red. And we'll start from the vertex. We start from the vertex of the triangle and we go to the midpoint of the opposite side. Everybody got that? Now guess what we're going to do here? Do the same thing. That's easy to find the midpoint. Just put a dot right there. And hopefully this works the way it's supposed to, because I was fairly careful, wasn't I? Look at that. Dead on, isn't it? Yep. Alright, so there you go. So what do you think? Well, I shouldn't say what do you think about this, the name of this word, because you would have no clue what you name it. But it does have a name, all right? It does have a name. Remember, the circumcenter was found by finding the perpendicular bisector of the sides. The incenter was found by finding the bisector of the angles. Okay, this thing is found by finding the intersection of the three what? Medians. Okay, we found three medians here, didn't we? We went from the vertex to the midpoint of the opposite side. They all intersect at that point right there. And that point right there has a special name. It's kind of weird looking. It's the coolest name out of all of them. It's called the centroid. Doesn't that sound cool? So that point right there is the centroid. How is the centroid formed? It's formed by finding the three medians, the intersection of the three medians on a triangle. Okay? Yes?
I understand like how you did that, but what's the difference between that and the incenter?
The incenter was the bisector of the angles. This is not necessarily bisected. See how that's a little skinnier than that one? We didn't bisect the angles on this, did we? Okay. Well, we didn't go straight down. We bisected the vertex. Or, yeah, we bisected each angle. Okay? So this right here is not being... we're not bisecting the angle. I never said we're bisecting the angle here. What do? We started from here and we went where? To the midpoint, okay, of the opposite side. So that means that this side and this side are equal. This segment and this segment right here are equal, and this one are equal. Agreed? Okay. Right. It doesn't mean that anything's equal to each other or anything else. Let me do... Oh, this is a crazy one. Watch this. This is pretty interesting. You know how all the other ones had something special about it? Remember that circumcenter? What was special about that point that was the circumcenter? It was equidistant from the vertices, okay? From the vertices, right. What was the incenter? What was special about that point, the incenter? It was equidistant from the sides of the triangle. Okay, this is not either one of those. This is not equidistant from the three vertices. It's not equidistant from the sides. Watch this. Let's label this. Let's call this A, We'll call this B, C, D. We'll call this E. Oh, well, that's all right. F and Q. All right.
Why did you do Q?
Because he said Q. All right, so let's take a look at this. Look at A, Q, and look at Q, B. There's a relationship between those two. I'll just put some numbers here. Is that all right? Let's make this little one right here. See the shorter one? Let's make that 2. Then AQ is exactly twice as big as the shorter one. So the longer one, because they tell us. There's probably a proof for it, but to tell you the truth, I don't know what the I don't know if they prove it or not, and I don't know if I could prove it if I had to tell you the truth.
I just wanted to know where you got the number.
Yeah, I don't see on here anywhere where it says to prove it. So there probably is a proof for this somewhere. I'm just not really sure. So I can't. I would like to. I would really love to very easily just say, oh, this is why this is twice as big as this. I would like to do that, but right now I just can't do that.
It's just
So just yeah, just know it. Okay, so this is 2, and this is what? 4. Everybody see that?
And every time it will be twice as big.
It's always twice as big. So where is it? Where is the longer side? The longer side is from the vertex to the centroid. Everybody see that? So from the vertex to the centroid is the longer one. That's twice as big as it is from the centroid to the midpoint. Everybody got it? Same thing with all the rest of them. Okay, so let's just make some numbers up. Let's say that's 3. So if this is 3, what's CQ? Then it's 6. What if I said ED was 10? What would you say EQ was? It would be 5. Everybody see that? What if I told you this? What if I told you the whole thing? Now let's pretend we don't know this is 5. I know you do, but what if we said that the whole thing is going to be a little messy, but that's all right. Let's say that whole thing was 15, and that's all they told you. Could you find an EQ and DQ?
Yeah.
Okay, divide by 3. Good, because look, this is twice as big as this, right? So if I divided this one in half, wouldn't it be the same as this? Then we have 3 equal parts. Would you agree with that? All right. So really, this is a third of the whole entire thing, right? And QD, right, and it's 1/2 of QD. But let's think of the whole thing right now. EQ is 1/3 of the whole thing. QD is what? 2/3 of the whole thing. Make sense? So if I told you the whole thing was 15, how would you find, let's say, EQ? EQ would be the easiest one. EQ would be 15 what? Divided by 3, because it's 1/3 of the whole thing, which is 5. Once you get this one, then you can get the second one pretty easy. Or you could have done this. What's QD of the whole thing? What fraction of the whole thing is QD? It's 2/3. So you could go 2/3 of the whole thing, right? And it's still the same thing. Watch, that goes 5 times, that's 10, and it works out perfect, doesn't it? So there's a lot of different ways to look at it. Okay, I think the book says, whoever's clicking, just stop. I think the book says the 2/3 thing, yep. But you could look at it all kinds of different ways. The shorter one is half of the longer one. The shorter one is 1/3 of the whole thing, right? Or you could say this longer one is twice as big as the short one. Or you could say the longer one is what? Of the whole thing. 2/3 of the whole entire thing. You get it? It's pretty easy, isn't it? Okay, and you can say the longer one is twice the short one is half the longer one. There are all kinds of ways you can look at it, decide what they are. But that's true about a centroid. Pretty cool, huh? I wish I did. I'll have to look to see if there is a proof that's fairly easy. But I'm thinking that maybe Salman Khan does it on his website, because he does quite a few of these types of proofs. Salman Khan, not today, because Sal is short. His name is Salman, yeah, but it's Sal for short. Oh, is that right? 36. They probably, let's see, exercise 36. They probably just say prove it. 36. Let me see. Oh, they do give you some hints. Okay, yeah, they give you a whole bunch of hints. It's on the top of 340. Not today, but maybe another day. We'll do that for fun, okay? And we'll prove that. So yeah, on the top of page 340, they kind of give you some ideas Yeah, we'll do it for fun. Okay. Maybe we'll do it the day we have Christmas break, before Christmas break. That'll be our fun day. Or when we have our parties, we could come in here and we can prove the Centroid.
We should have a Christmas party in here and we can prove that. He was a teacher.
If what? If I was...
Nothing.
Alright. Let's do another...
A Christmas party.
A Christmas party? I don't know. Is that right? We could do cool things on here.
Yeah, and you can show up.
Alright, let's do this one. We got another one. It's the same triangle, but here's another one. This is the fourth one we're going to do. And this one is called, I think I've used this word before. This one is called the altitude. Altitude. Do you remember what the altitude is? Yeah, it's how high something is. Here's the ground right here, and here's my cool airplane. Remember me drawing the airplane? Did I do that in here? And then the pilot gets on there, and he does his pilot voice. You ever hear his pilot voice? Oh, welcome, ladies and gentlemen. He always talks like that, doesn't he? Don't they always talk like that? He says, yeah. He says, oh, we'd like to welcome you to Hamrick Airlines. We'll be cruising at an altitude of, right? Well, what do they say? We'll be cruising, listen, we'll be cruising at an altitude of whatever feet, like 20,000, 30,000 feet. So when they say altitude, what are they talking about? Are they talking about the distance from here to here? No. Well, that's the ground to the plane. That's the ground to the plane. That's the ground to the plane.
Oh my gosh, look at my plane.
Say it. Alex, say it. Perpendicular. Perpendicular. All right, we're getting all wound up just because I have a silly picture and I made a silly noise, okay, or silly voice. All right, so just watch. So what does altitude mean? Altitude means it's the perpendicular distance, doesn't it? Okay, so here's the altitude. Let's do this. The altitude, again, is from a vertex. You want red? Red. Watch. If you go from here, listen now. The altitude is taken from the vertex, not to the midpoint, because that would be the median. From the vertex, where? Perpendicular. Okay, yeah, don't just say straight down. It's perpendicular to, well, the opposite side, we'll say. Okay, because it's not technically the base, because any one of these could be the base. All right, so it's from the vertex perpendicular to the opposite side. Everybody got that? Okay. Again, I'm just going to eyeball it, as we say. I'm sorry I say it weird, but why does that sound so weird? Eyeball? What do I say? Is it the ball or the eye?
No, you stress
eyeball.
eye. You stress
Eyeball. What am I supposed to say? Let's eyeball it. How's that? Does that sound better? Let's eyeball it. It is supposed to be. It's not at all?
Not at all. No.
That doesn't look perpendicular? Scooch it down?
Yeah. Keep going. Oh, yeah. That looks a little better.
That's good.
Little.
Oh my goodness. Alright. See, I've rubbed off on you guys. You guys are acting like me now. Now watch, if I went perpendicular to the other side, guess what it's going to do? Is it just going to go like this? What do you think it's going to hit? It's going to hit right there. Okay. It's not a centroid.
Orthocenter.
Yes, you read ahead, didn't you? Okay, look. So that point right there. And what's kind of cool is that you do this thing to all these different figures, and they meet at that common point. What do we call that common point that they meet? Or, I'm sorry, I shouldn't say that. What do we call any lines, more than two lines, three or more lines that intersect at one point? No. Any three lines that meet at one point are, say, they're what kind of lines? Concurrent lines. So every one of these, we've done 4. Shh, settle down now. I know this is exciting stuff, but you gotta settle down. So look, all 3 of these lines, or I'm sorry, all 4 of these figures that we've been drawing are concurrent, aren't they? And each of that point of concurrency has a name for each one of these. This one is kind of weird. We call this the orthocenter. Orthocenter.
I don't get what the difference is because they're both centered, aren't they?
Well, how do you get them? It's how you get them. We got this by going perpendicular to the opposite side. How did we get the centroid? How did we get the centroid? We went to the what? To the midpoint. So I could if I wanted to. I'm not going to do this because make it really messy. But if you wanted to, you could take a triangle, draw them all, and see the difference where those points are. Those points will be at different places on this triangle. Now, you know how there was always something special about that point? There was something special about the circumcenter, the incenter, and the centroid. There's nothing special about the orthocenter. So he's very sad. Okay? Tear. Here, this is tear. Okay, it dripped down his face. So he's sad because there's really nothing special about that point right there. The only thing special basically is that it's concurrent, that the lines are concurrent. They do meet at that point. It's called the orthocenter, but it's not equidistant from anything. It's not, one side's twice as big as the other. None of that stuff is true. It just meets there, and that's nice. Okay? Actually, there is kind of something cool about it. You want to see?
Oh my
You
goodness, Tim.
You won't see. Listen, you won't see it on this thing right here, but I'll show it to you live and in person. Let's put the homework on there.
We learned the Orthocenter.
Learn all kinds of stuff. What are you kidding me?
All where it's hitting the opposite side. Would that be called like the altitude?
This point right here?
Yeah.
Nah, it's just a point. This is like the distance from the vertex to the opposite side, I guess. Because there's nothing special about the orthocenter, but there actually kind of is. So maybe we'll turn that frown into a smile. Okay? It's like a Pearhead. That's Mr. Pearhead. He's my famous character that... Okay, so 3... You guys are wound up today, boy. Okay, 3, 3, 8, 3, 3, 9.
Like we're reaching insanity because we have...
Is that what it is? It's too early. It's too early to reach insanity. Wait till at least next week before we reach insanity. All right, so there's your homework right there. Let me show you a little demonstration real quick of this thing. When I draw the altitudes to the opposite side, I think that's what it is. We'll see. All right, so there's your homework. Have fun.